Welcome everybody on Zoom, welcome everybody in the lecture hall. Today we will finish, hopefully, if we are lucky, the part on querying the normalized data and JSONic and RumbleDB. So as a reminder to make absolutely sure that this is clear to you, why the reason why it actually exists is that in the beautiful world of relational tables, we have SQL, undisputed. However, as soon as you start to nest things and want more complicated use cases, and you go for heterogeneity, extra value, missing values, or values of different types within the same column, you start getting problems. Of course, you do have a few patches in relational systems with, for example, variant types for the heterogeneity and with the array or struct types for nested values, but it only brings you so far. So you need query languages for that. And the trick that actually makes it work is to no longer think in terms of tables, but in terms of sequences of items, of which tables are a special case. A relational table is just a sequence of objects that are flat and that are valid against the same schema, but you can go more to the left for single items or sequences of integers and so on, or to the right with fully unstructured and heterogeneous sequences. All right, so this is the trick. So it's a generalization of relational tables to data frames, but even beyond data frames to pretty much anything heterogeneous. We saw last time that the equivalent of the select from where expression in SQL would be the flower expressions in JSONic. We saw that they are more general than select from where, because select from where is always exactly select from where group by having, order by, limit of set. But in JSONic, flower expressions start with a for or a let, they end with a return, and then in between you can put whatever you want in any order and any number of times, right? So it's fully generic, and the way to visualize things, it's only a visualization, is that the flow goes top down in the flower expression, and you basically can visualize this as tuple streams that flow from clause to clause, right? So every clause takes an input tuple stream and gives an output tuple stream to the next clause, right? And then return finally returns again a sequence of items. What's very important in terms of formatting, try to take the habit when you write flower expressions to always align vertically your clauses, right? If you do for, let, where, group by, order by, blah, 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 return, make sure that all your clauses are aligned vertically. Exactly. Do not put tabs, extra tabs, or change the indentation between the clauses. Exactly like here, you see for, group by, return, they are aligned. The reason for that is that, as you know, it's a Lego game. So you can have a flower expression in a flower expression, in a flower expression, in a flower expression. So by aligning vertically the clauses in the same flower expression, you're doing yourself a favor, because then you know exactly what's happening, and you will immediately notice if something's wrong. For example, if you have a flower expression with no return clause, then obviously that's a syntax error. But if you align vertically, then you will see immediately if the return clause is missing. All right. Then we left with the types that you can actually declare types on sequences of items. So these are sequence types. And we saw that a sequence type is made of an item type, string, objects, array, integer, date, and so on, plus a cardinality indicator, which is the cardinality of the sequence. Can be nothing, then it's 1. Question mark 0 or 1, star is 0 or more. That's the fully generic one. Plus is 1 or more. The most generalized sequence type is item star, a sequence of item star. Okay. So this is another example of a query. So this is where we left last time, that this is new now. What's going on here? I'm creating a histogram with a group by query. So I'm looking at all the GitHub events, and I'm looking at the number of commits for each event, using my little trick so that if there is no array, it's setting it to 0. So this is here a little trick that, as I explained to you, but basically this is the number of commits in each event. We group by the number of commits, we order by the number of commits, so this is ascending, and we return here the grouping key plus an aggregation, right? So technically, in fact, that sort of things you could do in SQL, right? It's just a similar group by to what you would do in SQL. This is basically the select equivalence, this is the from, and so on. However, this is where it stops. In SQL, you don't have that kind of flexibility. So what's going on here? What I'm doing is that now that I have a commits and counts output here, I would like to validate it, because by default, you're not validating against anything, right? So here we are saying that there is this type histogram where commit is a short in the sense of integer type, right? Like in Java, a short and a long, it's just for the purpose of showing to you. So this is a short, you see here, and this is a long here. What you have here is a JSON schema. This is what we saw in the data modeling lecture. So you just put exactly this compact syntax of JSON schema right here. And it's very intuitive. You see, it's very similar to the pattern that you see here, but as values, you have the names of the types, right? So this is the type local histogram. And what I do is I take my query and I put it inside a validate type expression. So it says validate type local histogram star. It's a sequence of my little what to call the bulks on the histogram chart, and I'm validating that sequence. So it means that everything will have to be a short and here a long, and if necessary, you cast to a short and you cast to a long. So this means that now you have technically a data frame behind, right? Because you have one column commits, which is of type short, and a column counts of type long. So here it's output as JSON on your screen, but it's actually a data frame. And so what's nice is that then you can export it once it's a data frame to a structured format. We've seen plenty of them. There's CSV, there's Parquet, Avro, and so on. And with Spark, actually, you can export that back to another format. So if you don't want to export it to JSON, but to something else, in this command line, so here I'm using the big jar command line here, I'm running the query.jq that is right here. That's the one I had, run query.jq. And then I'm saying that I output it over there. I overwrite, this is just in case it already exists. Number of output partitions, this is just to coalesce them to just one. Output format CSV, it's going to create a CSV file. And I'm setting header true so that commits and count appear on the first line of the CSV file. This is what I'm doing. For whom is that clear? Okay. And then once it's output, you can go ahead, open it, and actually open it in a spreadsheet, and go ahead and visualize. You can also use Python visualization libraries. Python is really good at plotting things, and go ahead. So you see how it's interoperable with other technologies. So again, the only prerequisite, if you want to output to CSV, or you could put Parquet also here, is that you make sure to validate against a structured type, because you need to make a data frame. If it's not a data frame, then it's not going to be able to export to CSV or Parquet, because you need a schema to export to CSV or Parquet. Right? Yes, we have a question over there. Maybe you could throw the catch box.
Yeah, what if with the type that we declare is nested, and we say that the output? Hello?
Yes. Mm-hmm.
What if the type that we declare is has some nested value or nested objects, and we output it to CSV?
Then it will not work. If you output to CSV, it cannot, because it has to be flat, right? It might be that it tries to squeeze it in some way, like as a string or something, but you shouldn't. If it's CSV, you should only have a flat schema. But Parquet, you can have nested types without any problem. You could have, for example, an array of shorts. So you just add these square brackets around the shorts, and then you get nested data. Parquet, it will work, right? But then this is everything we've learned, right? You know that CSV is supposed to be flat. You know that Parquet can accept nestedness, but not heterogeneity, and so on and so on, right? So it's really a direct application of everything we've learned in the data modeling lecture.
So the chart is just error.
I think it's likely. We can try it out. I'm very careful whenever sometimes you're surprised by systems like Spark, because sometimes they will not throw an error, but just force it with a hammer, and this is why I'm careful saying that it might also be that Spark is somehow trying to squeeze it into a string or something, like it does when you open a data frame. But we'll test it actually, and let you know if that would be an error with a nested type, right? Okay. All right. So this is what I wanted to show you. So you can use this tool, RumbleDB, to convert between formats. If you download a data set in JSON, then you see some structure with the schema discovery that we saw last time. With exploration, you notice that there is a structure. Then create a schema, validate it in a RumbleDB query, right? Just validate type and inside JSON file. And then you use the command like that so it's run to run a query, and then you output it using similar commands to export it. So it's a Swiss Army knife to convert from format to format. And once you use Parquet, you can use Parquet file to open it, but it's going to be much, much, much faster with Parquet file because that's less to read on the disk. It's more compact, it's compressed, and so on and so on. All right, so now it's time to tell you a bit about physical details of the implementation of RumbleDB. But I'm going to note that since you asked so many good questions in the previous hours and last week on the physical level, you actually already know a few things on the physical level, right? I did not intend to actually already give you these details so early, so last week and so on, but I did. So now, maybe what I'm going to tell you now, some of it might be a repetition of what I've already told you last week, right? So this is now the mystery of how RumbleDB is implemented. So I'm going to start with pretty standard stuff. Almost any engine actually follows a similar pattern in the architecture. First, you have the query, which is in a text file somewhere, unless you write it on the shell. Of course, you can also write it in Jupyter Notebook or on a shell, but it can be in a text file. So you parse it. Then you get an abstract syntax tree. For whom is that familiar? Okay, that you've seen in other lectures, right? With context-free grammars, you can come up with a grammar and parse it and so on. And there's plenty of tools that allow you to do that, right? And then there's LL, LR grammars and so on and so on. Okay, so now we have an abstract syntax tree that is a tree representation of the query, but it's very raw, right? It's exactly just what was written. The second step is to convert this abstract syntax tree into an expression tree. It's going to be a bit similar in spirit, a similar structure, but the expression tree is a bit more abstract than the abstract syntax tree. And the expressions tree actually has a limited number of components. As I told you, in the case of RumbleDB, it's less than 40 different expressions. We have less than 40 different kinds of nodes in there. And then you assemble them, and this gives you the expression tree. The expression tree is not executable. It's only a representation. It's sometimes you would call it an intermediate language, IL, in some processors, intermediate language that gives you a representation of the expressions. It could be seen as a query plan, right? And then what is typically done is that you do optimizations at that level. Many engines iterate on the expression tree, look for inefficiencies, and modify the expression tree to make it more efficient. An example of that is what I told you last time. Imagine you used an equal sign instead of EQ. Then if the engine is able to detect that on the left, it's exactly one item, and on the right, it's exactly one item, then this will be changed, and the equal sign, or what's called the general comparison, will be changed to a value comparison, EQ. And that's done by iterating on the expression tree, and you just apply all of your rules. Of course, the number of things that you do depends on the maturity of the system, the number of years that you've spent on it, the number of customers that you have. The more $1 billion you have to throw at it, the more optimizations you can do, right? This is a bit how it works, but it's never ending. This is an undecidable problem. You're never going to be done with optimizing things. Okay, then the next step, once you have this expression tree that is optimized, you can do what's called code generation. You transform this expression tree to a runtime iterator tree. A runtime iterator is executable. That's the difference. These iterator trees contain the codes to actually execute these expressions. So you convert it. It's a very similar structure again. The difference is again that on the left, it's compile time. So this is just static information. On the right, you have the actual runtime with all the codes, right? So you have a runtime iterator tree, an iterator tree. Okay, so this is it. Now, what happens on this iterator tree? What is the flow in there? You should see it as a flow. What happens is that if you have expressions, then you have sequences of items flowing, right? Sequences of items. But between clauses, we saw yesterday that it's not sequences of items, it's streams of tuples. Right? Between the clauses, you just have the variable bindings that flow. So this is why you have two colors or two kinds of arrows in this runtime iterator. you have at some places sequences of item, right? The return expression returns a sequence of item, count takes a sequence of item, JSON file returns a sequence of objects, variable name returns the sequence of item bound to that variable, and so on and so on. Object lookup returns a sequence of item. But here, this is Flower. You have a for clause and you have a return clause. So between the for clause and the return clause, it's the bindings that are flowing. So this is why you have a tuple stream or a stream of tuples. So two possible colors of edges in this graph. You have the sequence of items and you have the streams of tuples. For whom is that clear? All right, so it depends if you have expressions or clauses. All right, now, what I haven't told you is how we execute things. Now, because this is just the abstract view of the runtime iterator. It turns out that there are plenty of ways that you can execute things. And now I'm going to give you the intuition of various strategies to execute an iterator. For example, imagine that I have streams of tuples. So I have my for iterator that generated the binding of $i. So I have $i in some collection, and that generated 5 bindings, right? In the first one, $i is bound to an object field 1. In the second time, $i is bound to field 6 and so on. So this is a tuple stream, right? That binds $i in turn to different items. Now I have to take this and return them. Imagine that I have returned $i, right? So one strategy would be to consume all of the incoming tuples with variable bindings. I just consume them, I collect them and materialize them. Materialization, that's the word I've already used. So I'm going to iteratively collect them, all of them, and retain them in memory somewhere. Maybe build a huge list or a huge vector or a huge array with all of my tuples, right? And then once I have done that, I'm going to output the results. So in that case, so it's not return $i, it would be return $i.field would be the query. And then I output in a single go 16432, right? What happens here is that I materialized things. So it's like you have a dam, like you have in Switzerland with the water. You retain everything as you would in a dam, the water, and then you open the dam and let the water flow, right? But then, as you can imagine, that can take a lot of memory, because imagine that you had a collection with 1 billion of items, and this list here of a tuple is actually has billions of them. As you can imagine, the amount of memory you would need, because this is on a single machine, the amount of memory you would need to do that is enormous, right? So there's a better way. In that case, we can actually stream, exactly like Netflix. So what we can do instead is to do it one at a time. I take my first binding that binds $i to field 1, then I do this $i.field gives me 1, and I output 1. And then I forget about this one, that's done. I've forwarded it. Then I take the second one, I compute $i.field gives me 6, and I ship 6, and I forget about it. Then again, the next one, 4, and I ship 4, and I forget about it. Then I take 3, I forget about it. Who sees that this needs constant memory? Because you only ever have one tuple at a time, ever. You never materialize. You never have the materialized tuple stream anywhere. Okay, then it's just consumed. But of course, it can take a lot of time, right? It would work. The memory, you don't need much memory. You could do it maybe with, in that case, to exaggerate a little bit, maybe 500 kilobytes of memory would be enough. But it takes a lot of time, because you have to iterate and iterate and iterate and iterate and iterate and iterate billions of times in order to actually consume the entire tuple stream. So as you can imagine, this is not really nice either, right? But don't forget, we're still on one machine here. Can we do better? Absolutely, we can do better. We can parallelize. So now we can take our billion streams and have them on multiple machines, just like blocks in HDFS or even the splits and the tasks in MapReduce and Spark. And now we use multiple machines in parallel. And then on the first machine, we have 2 tuples in that case. In practice, it's more going to be like thousands in each task, or hundreds of thousands maybe. So here we output 1 and 6. And on the second machine, we output 4, 3, and 2. It might be that within the machines, you're streaming, right? On the first machine, you're streaming 1 and 6. On the second machine, you're streaming 4, 3, 2, but you're spreading over multiple machines. This here is exactly the idea of tasks over slots in MapReduce and Spark that we've already seen. It's exactly the same idea. So this is a third way of executing the iterator. You see, whatever way we use, the result is the same. We output 16432. But we saw 3 different strategies to actually output this. And this is how RumbleDB works. It's seamlessly switching and picking the best strategy. Yes, the catch box is there.
What if we would instead maybe batch these things? Like what if we would batch this instead? So we would have a windows of a fixed size, I don't know, 10 or 100 elements. We compute all of them at once, and then we stream those instead of doing one by one.
Yep. So in fact, this is a little bit what happens with the notion of task that we've seen before. So what happens indeed is that you batch the streams, or it would be the same with items, with a sequence of items. You batch them in several thousands, several tens of thousands. That's one batch. And then you spread the batches as tasks over the machines. This is what happens. But what happens within one batch, whenever you can, is streaming. Within one batch, it's just a streaming thing, right? Okay. Is the order preserved? Yes. Spark preserves the order. So in that case, you would know if you have tasks, you know the order of the tasks. And so the output of the task is concatenated in order of the task, right? Does it answer your question? Zoom? Yeah, awesome. Okay, so that of course can take a lot of machines, but there is no free lunch, right? You know, you're computer scientists, either you take a lot of time or you take a lot of space, but there is no magic here. Yes, there is a magic, is that the price on the cloud is the same. Taking 10 machines for 1 hour is the same price as 1 machine for 10 hours. That's a free lunch. Use it. That's one of the very few free lunches you ever get.
Question on Zoom is, how is the order preserved? I assume all machines are returned simultaneously.
I didn't get the second part.
I assume all machines are returned simultaneously.
Yes, but you have to distinguish between the imperative execution and the functional execution. While it is true that there is an order in which the output items are computed, you still have a spatial ordering due to the semantics of the language. So even though you might have computed, let's say, the second batch before the first batch, you still know that in terms of semantics of the language, the first batch comes first. So even though you might have computed some items before others, at the end, you always order it in order of the batches, and then within a batch in order of the items and tuples. Does it answer your question?
So the answers are aggregated after everyone finishes.
Jein. If you allow me to use some German, jein. The idea is that it can be, if it's small enough that you materialize it. For example, imagine you put an array, square brackets around, then you will force a materialization, and then you will force an aggregation. But you cannot do that if that's a billion. What typically happens at the end of this execution is that there will be yet another expression consuming these billions items and returning billions items, then yet another expression. So you never ever materialize things. You keep track of the order logically because you know how to reconstruct the order, but you don't really materialize the sequence because it's too big. But if we go all the way to the end, what happens to the end? Very often, what's going to happen is that you write it back to HDFS. So when you write it back to HDFS, what happens is that every batch of output is going to be written to one file in HDFS. So if you have 1,000 batches, that's creating 1,000 files in the same output directory. This is what happens. It will even do that on your own machine if you do it on your laptop. So you see, if it's on your local file system, you will actually have a materialization on a single directory of everything. But if you write it back to HDFS, it looks logically like a materialization because on HDFS, you have these 1,000 batches with the content in order and the batches are ordered. But in reality, you know that physically, all of these batches are in blocks spread all over the cluster. So it's not actually aggregated anywhere, right? It's really over a cluster of machines. Does it make sense? Okay. And in some cases, for example, if you build a histogram, it might be that you have a group by in the process and you have only 10 groups. So even though you had 1 billion items in your input, you might have only 10 items in your output. Then you can just print it on your screen, right? Or export it locally to a CSV file. And then you actually aggregate and materialize because it's small enough, right? So you see, it's really doing everything. Depends if it's big, if it's small. You can output to HDFS, to your screen, to S3, to your local file system. It's just common sense. You will not output something with 1 billion items to your own file system unless you have a lot of patience, right? Okay. So you see, you can do S3, HDFS, HTTP, but of course, HTTP is read-only, as you can imagine. It will be a single download, so no parallelism for HTTP. The local file system, Azure, Google Cloud Storage, we didn't test, but I'm pretty sure it will work because Spark does. The format, JSON, CSV, Avro, Parquet, root, that's for physicists. They love using the root format for high energy physics, libsvm for machine learning, and so on. Okay. So these are all the formats that you can output to and read from. Now, a few more words, more in details about these modes of execution. I already told you, you can materialize, you can stream, you can parallelize. More exactly, you can statically, at compile time, you can already guess the strategy of runtime very early. For example, in the first case, you know it's the empty sequence. So you won't have anything in parallel here. You just output the empty sequence. It's a method call in that case. On the right here, you have an addition. You also know this is going to be a single item. So it's just a simple method call. You call the method, potentially providing any variable values if you have variables there, but you get one value. It's a Java method call, literally a Java method call. In that case, that returns multiple items, but not so many of them. It's just 4 of them. What's going to happen is called the Volcano iterator pattern. Who knows that? If I tell you what it's like, you will automatically recognize it, I'm sure. This is when you have an interface, an iterator interface with open, has next, next, close, and maybe reset. Who's already seen that? You've seen that it exists in Java, in C++, you can iterate. So open, has next, next. And so what happens is that every runtime iterator here is going to offer an API with an open, has next, next. And what you do is open, has next, yes, next, 1, has next, yes, next, 2, has next, yes, next, 3, has next, yes, next, 4, has next, false, done. Okay, so this is a Volcano iteration. This is actually streaming when you do that. You're streaming your way through, and very often it's going to be very efficient because you also stream through from the inputs, so you don't materialize anything. But as you can imagine, there are exceptions because there are a few constructs in the language. For example, when you have a group by, as you can imagine, when you group or when you sort, you cannot just stream. When you group, you have to materialize somehow the groups. When you order, you have to materialize in order to be able to sort, right? So streaming through is very often possible, but not always. You still have the Volcano iterator, but what's going to happen is that you might materialize inside of the iterator all of the inputs, and then once you're done, start outputting the items, right? Okay, so that's Volcano style. And on the right, that's also a Volcano style. That's a predicate iterating over a sequence of 1 to 10. So the predicate is also going to consume with open, has next, next, 1 to 10. And it's going to output with open, has next, next, the odd number. So here is going to filter out every other number. Okay, for whom is that clear? That's the local execution, local, that's on a single machine. Okay. Next, you have parallel execution when you try to open a JSON lines file like this, persons.jsonl. There are some, for example, in the exam, in past exams, we have plenty of files like that, one object per line. You've already seen that. What this does internally is that it's creating an RDD. Right, it's going to create an RDD, and it's an RDD of items, but using the polymorphism with a class item in Java. So it's an RDD of item. You've already seen RDDs when we studied Spark. I told you that RDDs can be RDDs of anything, including polymorphic classes. So it's an RDD of items. Why not a data frames? Well, you can see it doesn't fit in a data frame. Right, the columns are not always the same, and so on. So this is why we do an RDD. For whom is that clear? Okay, so this creates an RDD, but the user doesn't see it, right? The user will just see sequences of items. This is physical, what's happening here. And then imagine that you navigate dot countries. This is not going to be done with a Volcano iteration in that case, because we have an RDD. This is in fact going to be a flat map. So RumbleDB is automatically generating a flat map transformation on this RDD in order to navigate to the countries arrays there and flattens back everything. Flatten because sequences are always flat. That's the reason it's always a flat map. And a UDF, who knows what UDF means? It means user-defined function. It means that whenever you use the RDD API, you might supply lambdas. Who knows lambdas in Python? We've seen them, right? The Python API, PySpark. So here you need to supply a user-defined function. What is this user-defined function? It just contains some Java code in order to process these objects and extract the countries array. This is a UDF. But all of that is hidden. That's physical. Yes, you have a question?
Why do you call it a flat map if it looks like it is just a map? Like we just take every instance in the first array and then we take just the country field.
It would be a map only if you have the guarantee that every object has a countries field. From the moment that one object is missing it, using a map would no longer be correct because that would generate something with a null or something. The flat map is eliminating the anything that would be missing. So this is why it's a flat map.
Here we have a null.
Oh, yes, but this is a real null. I told you the difference between the empty sequence and the null, right? In JSONic, here it's a real null. This is a null item of type null. What I mean is really in the case that countries would be missing, which is not the case here. If countries is missing, then that would not be at all in there, not even as a null. Okay? Does it make sense? Okay. And of course, add any questions you want also offline, we are happy to answer them, right? So now I do my array unboxing. That's again a flat map. And inside the UDF, I have all the Java codes to extract the content of an array. Here, it's probably more obvious that it's a flat map, right? Because you see it clearly, there are several items in every array. Then distinct value would also be done as a transformation to Spark with the distinct transformation, you see. So this is how it all works. Now, imagine I don't use JSON file, but Parquet, because I did my homework of converting my data set to Parquet with schema validation and so on. And now I open it with Parquet file. It's going to be much faster. Why? This is because when you open a Parquet file, you know it's a data frame. So in that case, we don't create an RDD, we create a data frame. Data frames are much faster. So here we have inside a data frame. It's still a sequence of items, it's a sequence of objects, but physically now we have a data frame. So you see, in the case that it's heterogeneous, like this, potentially it's polymorphic with an RDD. And in the case that it's homogeneous, coming from CSV or Parquet, for example, then we use data frame. This is all hidden from the end user. The user only ever sees sequences of items, but they will notice that this is much faster and this is a bit slower. It's just a graceful degradation of performance, but with no loss of features. So you see, all of that, projection, selection, grouping, and so on, this is all implemented as data frames, data frame transformations on this tuple stream visualization, right? This is all nicely transformed to Java. And these are your colleagues, right? Your fellow students from the previous years who made this implementation. So as an example, imagine I read a JSON file that gives me an RDD. Then I iterate over it, so that creates a data frame, because that's now a tuple stream. So you have the variable person bound intern to these objects there. I'm passing the details that it's serialized to binary so that it fits in a single column, right? Creates a bit of a performance overhead, but again, that's a graceful degradation. Then the second four adds a column. Again, this is my visual that I gave you of the flower expressions. Remember, I told you the variable bindings in flower expressions can be visualized as tables. And in fact, these tables that you can use to visualize are actual physical data frames in the implementation there. So now we have this for country that adds a column over there, where is going to filter out whenever it's not US, right? And then let first name creates a new column and so on, and so on, and so on. And then you map it back to an RDD at the end. What's very important is that, again, all of that is hidden from the user. They don't see anything, but you followed the data modeling lecture, the Spark lecture, the MapReduce lecture, the data frames, and so on. So you actually understand how you can actually do that internally using RDDs and data frames and transformations in Java in such a way that at the end, you give the correct results to the user. All right? So for clauses, you have two ways of executing them. One in parallel with the data frames, which is what I just showed you right here. This is the parallel execution, right? If it's a very large data set like this, that would be in parallel. But if it's something very small, that's going to iterate on the tuple stream without any data frame, just because it's much faster, and this is going to happen locally. Okay. What about expressions? So this is for clauses, for tuple streams. And what about expressions for sequences of items? Well, I already told you these are simple enough that it's a Java method called directly. This is Volcano iterator model, open has next. JSON file creates an RDD, so you use RDD transformations. Here, Parquet file would be data frame, so you use data frame transformation. Plus, and that's something I haven't told you yet about, in some cases, we are even able to translate that to native Spark SQL in a hidden way from the user, but it will be super fast. If RumbleDB is able to actually convert, in that case, this expression right there to a Spark SQL expression to do it in Spark SQL, this is going to be super fast. Right. Okay, so you see, that's actually 7 different ways of executing things, and RumbleDB magically figures it out. There's, of course, a few rules that you do in order to do it. This is all decided at compile time. You decide on a plan, and then you go ahead and switch between the different strategies. Right. So this is what happens for every expression. You create, you infer the static types at compile time. You determine the execution modes. These are the execution modes. And then you compile to a runtime iterator tree, and then it's going to execute according to plan. Right. So this is just to, I don't want to scare you, but this is basically the sort of things that would happen in Java, right? You have this runtime iterator. You have these 2 colors that I told you about, streams of tuples or sequences of items right there. And what you add is, for these execution modes, you add little stamps there. You say, okay, method call, RDD, data frame, RDD, method call, method call, method call. Every time you specify what execution mode it's going to be at compile time. And then at runtime, you just pull the string over there, and everything is going to flow around according to the strategy that you have decided. Okay? So you see, for example, you can try as a mental exercise to imagine how this would be done, right? JSON file foo bar sum, and you will see, okay, JSON file, that's probably an RDD. Here it's an RDD flat map transformation, an RDD flat map, an RDD flat map, an RDD flat map, and here it's a sum, probably a reduce transformation over Spark, and so on and so on and so on, right? So you see, for the end user, this is just a JSON query returning sequences of item, but behind the scenes, this is everything that actually happens to make it execute very fast. Okay, so the big picture in here that we have is that JSONic is a language to execute on a so-called Lakehouse. Who ever heard of Lakehouse? Some of you. Warehouse, maybe? Warehouse, maybe more. So Lakehouse was coined last year in 2021 by the Databricks people, the same who created Spark when they were at Berkeley back then. And the idea is that it's a generalization of a data warehouse, but with more flexibility, and you cover everything with a data lake, but potentially with structured optimization more similar to a database system. And you can do machine learning, business analytics, data warehousing, and so on, all in the same platform. And so what RumbleDB wants to be in the end is a data lakehouse with JSONic on the top to do all of that. And yes, including machine learning, right? So this is the traditional view where you have either the structured data or the warehousing, and this is here, the lakehouse system, where what you do is you extend the data lake with additional layers that kind of emulates what you would have in a relational database system, like indices and so on and so on. Somebody asked yesterday, I think, about what do we have indices in a data lake? Normally not. You don't have any indices. You only have them in a full-fledged system. But in data lakehouses, you do have indices because you add extra levels on top of the data lake that add all of that functionality. This is cutting edge. This is the next generation of things that are now starting to emerge. And you see that now between the ETL systems and the data lake systems, things are starting to merge a little bit, right? This is all converging. Okay. In terms of performance, so this is in the publication we had that it competes quite well with other technologies. So the students basically did a great job at implementing the RumbleDB engine. Here is just, I wanted to show you an example of when you validate types and output it to JSON, CSV, Avro, Parquet, and so on, but actually already did with the histogram. So this is maybe a repetition. So you can basically create, using JSONic, a sequence of objects. You can validate that sequence of objects against a type. And if that type is compatible with data frames, if it's flat, you can export it to CSV. If it's nested, you can export it to Parquet, and so on. For example, you can also, if you have a messy input, you can clean up things a little bit to convert it to a data frame, but this requires work. This is very challenging in machine learning. This is a big problem machine learning people have when they have a messy data set. How do you clean it up? And the JSONic language allows you to do that. Yes?
Yeah, so I have a question related to the performance. Why that it is decreasing? So in the diagram showed before,
yeah.
Why is the performance increasing when the input, for some of the inputs, when they increase?
So the idea is that when you have structured data in data frames, you can compact it more. So you have less I/O in terms of bits that are flowing. You don't need to serialize and deserialize from binary because of polymorphism that forces you to serialize to a binary form. That's very slow. If you have data frames and you can convert to native SQL, then you don't need UDFs. UDFs are also slower. Having to pack Java code in a UDF and ship it over the cluster costs performance. But if you are in native Spark SQL, you don't have that. It's much faster. So this is the reason. Basically, as soon as your data starts to be polymorphic and irregular, it has to be slower because the execution techniques are going to be more costly.
Why is it slower to do some query on this data more? If you go back to the diagram for the graph that showed
This one?
but no.
Which one was it?
When you showed the performance of the different.
Oh, this one here?
House. Yeah, exactly those. So the input size that it increases, but
because the size of the cluster is constant. So the more data you have, the more it increases, right?
Yeah, but
at the start. This might be artifacts. Sometimes you also have artifacts on the cluster that you're lucky. It's a bit faster. It's a bit slower. I think that's the reason. It's just some irregularities. Right, you shouldn't pay too much attention to these fluctuations. Yeah. Okay. So this is here an example. I'm leaving that as homework for later. This is an example of cleanup query that takes a messy data set like this. It takes this messy data set, cleans it up, and then validates it against the data frame schema, and then you can export to Parquet. So again, that solves the cleanup problem that you take a messy data set, clean it up, and export it to Parquet, and then you can do machine learning on top. And finally, that's my final slide. It's an example of how you even have a machine learning library with which you can have estimators and transformers, and you have labels and features columns, and you can use machine learning models, train machine learning models and execute them. But this is out of scope of the lecture. I'm just telling you, if any of you is interested in machine learning, then you can also do that in RumbleDB. That was also a beautiful master's thesis that one of you did a while ago to add this functionality. Okay, so that's it. That was my last slide. Again, my advice is very simple. Download RumbleDB, use it, and query. At the exam, you will have it, but we'll release all the data sets of past exams. We'll also tell you the data set you'll have at the exam, probably GitHub archive. Go ahead and query. That's the best way to get familiar with what's going on. When you query, you don't have to pay attention to the physical details because this is all hidden from you, but it's still interesting to actually understand because since you know Spark and MapReduce, then this has no secret for you. All right?
Sorry, I have one question. I got a few questions in the exercise class regarding if there's any documentation, like syntax documentation during the exam.
We will give you the pointers. There is documentation on the syntax, there are tutorials, so we will give that to you. Yeah. All right, then it's time. Thank you very much. See you next week for the next lecture, probably on graph databases. Thank you.